Hello everyone, welcome to another GIS lecture video, and in this lecture video I want to discuss the final version of coordinate system called state plane. Now, state plane is in many ways similar to UTM, but it's at a very local level. So UTM took the entire Earth and broke it up into zones. Each zone was defined a central meridian using the transverse Mercator projection. With state plane, what we do is we do something similar at the state level. So state plane is a US only. I should clarify that up front, right? You will only find state plane in the US. Now, other countries may have similar systems, but the US specifically has something called state plane. And basically what state plane does is it breaks each state up into one or more zones, gives each zone a standard parallel, right? This is if it's an east-west zone, or a central meridian, if it's a north-south zone, right? And again, standard parallel and central meridian, right? These are just fancy terms for standard lines, right? If the standard line runs east-west, it's a standard parallel. If the standard line runs north-south, it's a central meridian. We've already looked at central meridians when we talked about the universal transverse Mercator system. State plane functions very similarly. So let's go ahead and take a look at an example for New York specifically. So this is the state plane boundaries for New York. And you can see that they sort of follow this idea of, political boundaries. That's not that important for this particular example. What is important to note is that there are 4 zones. 1, 2, 3, 4. Okay, right? And so if we think back to UTM, right, the idea of UTM was that we were trying to minimize the distance of any location within the map from a given standard line, whether it was a standard parallel for east-west or a meridian north-south, right? State plane takes that to another level, right? We now have a standard meridian for west, a different standard meridian for central, and a different standard meridian for east. And then for Long Island, because the orientation is north-south, we actually have a standard parallel running east-west. Right, so we've now taken the state and we've broken it up into 4 different pieces, which means that we're even closer to the central meridian here. And this is important to understand, right? Is that if the orientation is north-south, right, the standard line is going to be a central meridian. If the orientation is primarily east-west, right, then the standard line is going to be a standard parallel. And what that means is that we have 2 different map projections in play, right? If we have a north-south, right, standard meridian, these 3 here are going to be based on transverse Mercator. Note, I am not saying universal transverse Mercator. I'm just saying normal transverse Mercator, where we take the cylindrical projection, tip it on its side. We have a single standard meridian. In this case, the standard meridian cuts through this portion of New York, right? Again, we can use aspect to rotate the developable surface to match the area that we want, right? In this case, what we're going to do is we're going to rotate it so that it matches Western New York. So specifically, right, the standard meridian here, right, is at 78.58 degrees west, right? That is the longitude of this central meridian, right? The longitude of central, right? This right here, right? This is 76.58 degrees west, right? So we're rotating the universal not universal. We're rotating the transverse Mercator ever so slightly to set that central meridian, or the standard line, in the middle of this zone here. We're rotating it slightly more to set a different projection here. We rotate it slightly more, we set this projection here, right? So these 1, 2, and 3, these are different projections. So we have 4, I'm highlighting different projections just for New York, right? We have 4 different projections just for New York, okay? So what about Long Island? Well, Long Island actually has a slightly different basis, right? You can see here that we have a standard parallel instead of a standard meridian. And so what happens with this, right, is this one is actually based on the Lambert conformal conic. And what makes it nice is that this is actually a secant projection. Right? And so what does that mean? Right? What that means is, right, if I butcher Long Island, right, Long Island looks something like this. Right, what happens is we have 2 places where the developable surface touches the reference globe, right? We have 2 standard lines, right? And this is the case, right, secant case. So where are these standard lines? Well, the top one here is at 40.6. Sorry, the bottom one is at 40.6 degrees north. Right. The one up here is at 41.03 degrees north. Right. So you can see that the distance between these two is barely even 0.5 degrees, right? It's less than 0.5 degrees. So you can see that these 2 standard parallels are really close together, meaning that the distortion, right? Because again, distortion increases the farther away you get from a standard line. You can't get very far away from a standard line here, at least not in Long Island, right? So again, the point of state plane, the takeaway here, is that if we have a large north-south extent, we take a transverse Mercator projection basis, we shove that standard line, in this case a central meridian, in the middle of that zone, so that we're very close to that standard line no matter how far away we go. If we get too far away, well, we just rotate the transverse Mercator projection again aspect is a property. Plop a new standard line in a new projection. So if we're standing here, right, we wouldn't use the west projection, we would use the central projection. We start traveling, we get here. Well, we're too far away from the central, so we rotate the transverse Mercator again, create a new projection, and plop a new standard line, have a new projection, so that we're, again, not terribly far away from that standard line. If we go to Long Island, well, Long Island is a larger east-west extent rather than north-south. So instead, we swap out transverse Mercator. We use the Lambert conformal conic, which, just to recap so everyone's on the same page here, right? That's what I mean when I say Lambert conformal conic, right? We switched from the cylindrical to the conic projection. We create a secant, so we're squeezing this in so that it touches the developable surface twice. We set those standard lines on top of Long Island so that basically you can never be far away from a secant line, or I should say a standard line. So the idea here is that by creating several different map projections for each part of the state, we generate a system where we minimize the distance from the standard line at the local scale. Okay, so hopefully this makes sense. And as always, if you have any questions, please reach out. Thank you.